and enjoying the program for the Festival of Geology, and looking forward to everything that's to come. So I hope you enjoy this tonight. I've tried to keep it quite nice and broad, and I know that there's another event at 7 o'clock associated with that, so with the festival, so I'll try and get through in good time. So what I thought I'd talk about today is a little bit my own research, a little bit just general sort of interesting stuff, right, about the history of the atmosphere, and particularly because we have this interest in geology, what the rocks tell us about the history of air, and kind of what our understanding of that is, because it's a very, very in vogue area of research. You often will find articles about it on BBC News and The Guardian and all these kinds of places. So I thought I would talk a little bit about that and what our state of understanding is. And I just want to give a thank you, of course, to GeoBus, to the Scottish Geology Trust, and to my funders of my research, which a bit of this, the Carnegie Trust and the European Research Council. So why should we care about the air? Why should we care about the evolution of our atmosphere? It's a very valid question, and it's something we always need to keep at the forefront of our minds when we're doing any research, is why do we need to know this fundamental piece of knowledge? So over the course of Earth history, the composition of our atmosphere, the different gases that make it up, have exerted strong controls on our climate, and that has influenced the habitability of our planet, whether it's been warm enough, whether it's been freezing cold, such as during snowball earth events, which we'll touch on today. And the composition of different gases in our atmosphere in particular has rendered at certain periods, portions of the Earth, for example, its surface was habitable. And almost always, changes in atmospheric composition or in atmospheric processes are usually involved with each of the kind of mass dyings, mass extinctions, but it's not always a negative story. Changes open up new environments as well. And the evolution of our atmosphere in a kind of much less kind of exciting way than mass extinction events and that kind of thing, it has this kind of slow control and weathering and nutrient cycling, and that really affects how life has evolved, and the capability for life to reach different levels of complexity and different levels of total mass of the biomass. And so what we have here in the bottom right hand corner, which we'll talk about a little bit towards the end, some of my work on some Scottish rocks relates. This is a tetrapod, which is one of the first animals to come out of the water and to gulp lungfuls of the air rather than to filter it through gills in the water column. So what can rocks tell us about air? What are the properties of air that we can read from the geological record? And we can read a surprising amount. We can read about humidity, we can read about temperature, we can read about pressure, and we can read about composition. And it's the latter two that I'm going to talk about today, really, because I like to take this long view of atmospheric composition over long time scales, over billion-year time scales. And unfortunately, kind of the record that we can get about humidity and temperature is, in general, a little bit more limited in terms of time. But it's worth a tip of the hat to here before we move on to talk about pressure and composition. We can discern quite a lot of really cool stuff about humidity and temperature. And so on the right here, I have a figure from a paper by a former colleague of mine at St Andrews, Fernando Gasquez. And Fernando is kind of an expert on using speleothem deposits, cave deposits, to work out paleohumidity and temperature records, and to link that. He works quite closely with historians, he works quite closely with archaeologists, and to link that to things that are to environmental change on human timescales. So here, this speleothem deposit, actually, when you combine with the dating, which is what's shown in the yellow boxes, it spans the part of the Roman Empire era, and so you can actually tie changes in humidity with historical records of periods of aridity and periods of famine and ultimately collapse of some of these civilizations in regions, if not totally. where I work, mostly deeper in Earth time in the rock record, there are no scrolls to cross-reference with, and we are entirely reliant on the rocks. So that's what I'm going to be talking about mostly today. So what's in a gulp of air? What's in air? It's probably a good reference point before we start talking about how it's changed, as we talk about what it is now. Most of our air is composed of nitrogen. It's about 78% nitrogen. It's about 21% oxygen, okay, which we're all reliant on tonight as we sit here breathing. Argon is an inert noble gas component, constitutes about 1% of our air. And then actually, surprisingly, the gases that we maybe hear most about in terms of how they're changing and how that's affecting our environment and affecting our lives, the greenhouse gases, carbon dioxide and methane, they're actually really small component of the modern atmosphere, but they have, they may be small, but they have a large ability to affect and influence our planet's climate. Other trace gases that we have include hydrogen and other noble gases such as xenon and krypton. I'm really going to talk about 4 today. I'm going to talk about nitrogen, I'm going to talk about oxygen, carbon dioxide and methane. And it's actually been quite hard to kind of write a talk tonight because all 4 of these gases exist in kind of interlinked global biogeochemical cycles. And so it's kind of hard to find a good place to start and a good place to end because they're all interlinked. So hopefully we've got that. So let's start with, because it's the biggest, let's start with nitrogen. Now, nitrogen is important for 2 reasons. Nitrogen is a very important element to life. Along with carbon, hydrogen, oxygen, phosphorus and sulfur, nitrogen comprises one of the most fundamental elements for the creation of DNA, for amino acids, for proteins. So the availability of nitrogen on Earth for life and for it to be available in forms that life can use is really a very important thing to keep in our minds. The other thing about nitrogen is there's just a lot of it. And the consequence of that is that nitrogen is actually the principal gas that controls atmospheric pressure. So pressure on Earth is, in our atmosphere today is 1 bar. 0.78 of that is nitrogen, 78%. So how has nitrogen changed over time? Well, this figure shows what I think is probably the majoritarian view of how we think nitrogen has changed. And that is to say it has risen from quite low levels, and hopefully you can see this. The colors are not great, but there's sort of 2 faded blue boxes here. And there's a lower box and an upper box. And gradually we think that nitrogen and ergo atmospheric pressure has risen gradually over time. And the reason for that is linked to plate tectonics and subduction. So essentially that at active subduction zones, compounds such as ammonium are oxidized to nitrogen gas. And so nitrogen gas is chemically inert, and it's light, it's volatile, and so it escapes, it degasses at these sites of subduction. And so subduction arcs are generally sources of nitrogen. So as you can imagine, as plate tectonics, modern style plate tectonics has evolved and operated on Earth, and that's a very debatable subject of a completely different talk. That has controlled how nitrogen has escaped from the solid Earth essentially into the atmosphere and built up a reservoir there. And this also explains why this link to plate tectonics explains why some of our the amount of nitrogen or the ratios of nitrogen to different noble gases in our atmosphere and in our Earth materials, for example, the ratios of nitrogen to argon, of nitrogen to isotopes of neon are different with comparison to our sister planets Mars and Venus, and so we get this kind of sense that it's very much linked to plate tectonics, and it's been rising over time. This isn't, however, the view that everyone necessarily holds, and some have argued that nitrogen levels were much higher in the past and have actually been decreasing over time. Now, the reasons for that, I don't think the evidence for that is quite as strong, but I'm not an expert in nitrogen. I think much more about oxygen, which I'll talk about in a bit. But the reason that I think a lot of people are in favor of this is because it helps us with another problem that we face deep in Earth time and but relates to the composition of Earth's atmosphere. And that is the faint young sun paradox. Now, you may have heard of this before, you may not have heard of this before, but this was put forward by famous physicist Carl Sagan back in the 1970s, Carl Sagan and others, I should say. And this is kind of something that as geologists, okay, we spend a lot of time looking at our feet. Maybe sometimes we should look up and think about the sun, because on these kinds of timescales, stellar evolution matters. So back earlier in Earth history, the sun was less luminant than it was today because it had it was fusing it had a higher amount of hydrogen relative to helium within the star, and that's changed gradually over time. And the consequence of that was that it has become more luminous. So if you have a look at the graph on the right, on the right-hand axis, you should be able to see luminosity over time, 1 where we are today. And as you follow that black line back through history, back to 3-4 billion years ago, you can see that the sun was sort of 70 to 80% as bright as it is today. And that had a huge impact on temperature on Earth, because what you can see is that black line crosses a horizontal dotted line, which demarks in Kelvin the freezing point of water. And what Carl Sagan and others argued was, well, this is completely inconsistent with what we understand about the geological record and the record of life on Earth. And we know that it wasn't a frozen ice ball. There's sedimentary evidence of rivers, of deltas, of shore faces, and not, it wasn't the case that it was entirely frozen. So something must have been keeping Earth warmer than you would expect just simply by the evolution of the sun. And that they concluded must be our atmosphere, and in particular, greenhouse gases. So today we worry an awful lot about fluctuations and increases in the concentration of gases like carbon dioxide and methane. But back in Earth history, this was something to be celebrated, because the carbon dioxide and methane kept our planet warm. But how much of these gases, how much did we need to do that? Well, the answer to that varies depending on different modeling scenarios. And so proponents of high nitrogen in our early atmosphere like this idea, because it adds extra pressure into the atmosphere of the early Earth. The pressure can be more similar to it is today. And this means that we need slightly less carbon dioxide and methane to essentially solve the faint young sun problem. So this is great. This really helps with the calculations of this, but we are geologists and we need to think about what the rocks say, and do we have a record that could refute or confirm this? Well, the records that we have that exist for tracing nitrogen as a nitrogen concentration, basically by looking at atmospheric pressure changes, it's a wee bit patchy, but there are a couple of proxies that have been put forward and have differing degrees of acceptedness in the community. And one of the first that was put forward was this idea that we could trace changes in atmospheric pressure by looking at the diameters and the imprint depths of fossil raindrops. And in this case, these are examples from the 2.7 billion-year-old Winterstorp supergroup, ash beds within the Winterstorp supergroup in South Africa. And they were used to constrain atmospheric pressure between somewhere similar to today, but the authors thought much less, probably less than half of today's atmospheric pressure. And a similar group of workers led by the same main author followed this up a few years later by also within the Winterstorp group looking at the diameters of and the shapes and things of gas vesicles within pillow lavas, and they used that to conclude that again atmospheric pressure was likely to be much lower than today. And there are a few other lines of evidence, geochemical lines of evidence, that seem to be telling us that atmospheric pressure was much lower early in Earth history. Now, my colleagues at St Andrews, Sammy McHale and Aubrey Zirkle, have written a little bit about this, and they've tried to summarize it, and I've got this really good figure that kind of summarizes our current understanding of nitrogen from them. Essentially, we don't know. I mean, that's really the honest answer, and that's the one that I think has to be the sort of take-home message of nitrogen. We don't know whether it's gone up gradually or gone down. I think that generally speaking, the evidence seems to more so support that it has increased gradually over time. But Aubrey and Sammy proposed a couple of other cool scenarios. They ruled out this one on the right, I should add, that there's no evidence that nitrogen was going up and down and up and down and up and down. They said that was unlikely. But they introduced a kind of quite interesting sort of have your cake and eat it model, conceptual model in the middle, which was that nitrogen levels in the atmosphere essentially had an inflection point around about 2.5 billion years ago. They decreased from higher levels prior to this and increased afterwards. And they said that this could relate to the fact that that nitrogen, as it partitions into rocks, and the different speciation of nitrogen in the rock record is redox sensitive. And so that is going to change massively depending on how much free oxygen is present within the system. And so this is why it becomes difficult to disentangle these different gas stories from each other, because we're going to start talking about oxygen pretty soon. So they argued that after this period, which it's called the GOE, the Great Oxidation Event, that is when subduction zones first started acting as sources of nitrogen. And before that, they actually were sinks of nitrogen, and that this kind of approach could explain all of the evidence about the evidence sort of that would be supportive of high nitrogen levels supporting the faint young sun. And because the GOE is happening just a few 100 million years prior to the GOE is happening a few 100 million years after we're seeing those fossil raindrops and things like this, the decreasing nitrogen could also be explained here as well. So it's something worth thinking about. Basically, we don't know, but it is likely that changes in oxygen have affected changes in nitrogen. So let's move on and think about that next troublesome gas, and the one that I think a lot about probably most, which is oxygen. Now, oxygen is life's favorite gas, I think. It's produced by life through the process of oxygenic photosynthesis, which most likely we've all come across in school, but perhaps not. So basically what happens is that photosynthetic organisms today on Earth, most commonly plants, but way back early in Earth history, prior to the evolution of plants 400-ish million years ago, this would have principally been done by more simple organisms, and initially, of course, done by cyanobacteria. And so carbon dioxide and water in the presence of light are converted into simple sugars, with oxygen produced, free oxygen produced as a waste product. And so the first organisms to do this on Earth were the cyanobacteria. They lived together in communities, microbial mat communities, and those could form more complex structures, which are preserved in the rock record as, well, these kind of mounds that we see, and we call those stromatolites, literally layered rocks, stromatolites. And what we think they look like are, we have a few analogues in the modern day, not very many, but in Shark Bay in Western Australia, in the Hamlin Pools, you can see these microbial mounds growing, and they can only exist here because this pool is hypersaline, and it keeps all the little snails and gastropods and whatever that would graze these things into extinction, keeps them at bay. So you only find today these kinds of complex microbial communities in places of, say, high water current strength. That would be the example in the Bahamas, and also places like in Lake Vanda and Antarctica, in a landlocked lake underneath the thick sheet of ice. They really have to hang on in the environments where things don't exist that can come and eat them. But before the evolution of these kind of animals that could feed on them 500 million years ago, they would have been much more common across our shallow seas and oceans. And with so much space and with so much time, they were slowly transforming our atmosphere through this waste product of oxygen. When did they emerge? We don't know for sure. It's a very active area of research to try and pin that down. We have some direct lines of evidence. Microfossils first appear really around about 2.5 billion years ago. We think from a lot of indirect lines of evidence from, well, there's some questions about biomarkers, but with looking at trace metal concentrations in sedimentary rocks, and by doing some biological computations of sort of gene sort of molecular clockwork, we think that they had evolved by about 2.7 billion years ago. And it's important to note, of course, that once they had were producing lots of free oxygen, it allowed us to use this much more efficient. What we're all doing today, sitting here today, doing aerobic respiration, we're doing the exact opposite of that reaction. We're taking that oxygen, combining it with the simple sugars, releasing energy and producing carbon dioxide and water as a waste product. So how did our understanding of oxygen change? Because it was not really something I think that the original founding fathers of geology really thought about. They had this kind of approach of uniformitarianism that we know about, and that the present is the key to the past. And the idea that there was big geochemical change, unidirectional geochemical change that had happened in Earth history, I don't think really had quite occurred to them yet. That's not their fault, that's just how things evolve and change. So I think that the story of oxygen in our atmosphere and how it may have changed starts a bit earlier than most people think. There is evidence that from the late 1920s, a lot of workers from field geologists, from companies and from various surveys were starting to notice some interesting kind of temporal restrictions of certain features that they were seeing in rocks and what was just broadly termed the Precambrian. It hadn't really been subdivided, but they started to notice these things, and some of the earliest work actually came out of exploration companies and surveys in Central and Southern Africa. And so they began to notice some interesting features. One was they noticed grains of detrital pyrite, so iron sulfide, fool's gold, uraninite, the natural ore of uranium. And they noticed these within sandstones and conglomerates of a particular age, but they seemed to disappear quite quickly as you went up through into younger deposits. So there's some pictures of them here, and you can see that they're rounded grains. This is reflected light. This is what pyrite looks like. And here you can see these kind of inclusion trails here. Hopefully you can see my mouse, but you can see these kinds of inclusion trails, kind of bow-shaped, and that they're cut off at these rounded edges. And this is good evidence that these are detrital in origin. They haven't grown within the rock. They are essentially pebbles and small granules. And that shouldn't be, because in our atmosphere today, these are highly unstable. They quickly break down and oxidize to sulfate. But here they are in rocks around about 2.7 billion years old. So that was weird. The other thing they started to notice was that as they were going up through rock sections, rocks that were sandstones and mudstones and siltstones that were gray suddenly started to turn red. They started to have a deep staining of iron oxide minerals, of hematite and other minerals like this. And so this is the first appearance of the so-called red beds. This was on the title slide. This is a similar image of the same outcrop from Russia. And here you can see mud crack desiccations. They've been slightly strained, I think, but this is one of the first red beds. It's 2 billion years old, and it's really telling us that this iron is starting to be oxidized by oxygen. You can see this kind of feature in much younger rocks. I don't know if Emma Smith is here today, but she was telling me earlier this week or last week about some very similar mud cracks to this that you can see up near Gerlach, which are closer to 1 billion years. And you can see, you know, I mean, the red beds, for example, that you find in the cliffs at Arbroath and stuff like that, it's a similar process, but the difference being that it wasn't really unusual by the period that they were deposited, but it was unusual at this. These were the first evidence of oxidation of some of these minerals. These workers also started to see that there was a temporal restriction to some of the economically important units that they were looking at, things like banded iron formations, which continue to be one of our main sources of iron. We do have one little banded iron formation in Scotland, though it's been quite heavily metamorphosed, and it's a bit younger than these earlier banded iron formations. But the banded iron formations were really deposited up and until around what we would now understand to be the Great Oxidation Event. And what these workers also noted was that there was an association of all of this change with major glaciation on Earth, and they really didn't really have a systematic way of understanding this, and they weren't really necessarily talking to each other at this time. But between the 1960s and the 1970s, a group of workers started to emerge who were putting this together. Roscoe, but particularly Dick Holland and Preston Cloud, and they started to put this together, and they kind of twigged that this all had to do with oxygen in our oceans and in our atmosphere, and obviously it had changed majorly. And they proposed around about 2.3 billion years ago, and they didn't have access to the tools and to the expertise and all the systems we have now, but they really weren't far wrong. And the one thing that I'm glad that isn't part of their legacy is this term that they used for it, which was oxy-atmosversion, which is pretty clumsy term, I think. But they used this to refer to the fact that they thought oxygen had risen quite quickly at this time period. So for the next couple of years, sorry, this is kind of a texty, boring history slide, but I think sometimes it's useful to see how ideas have changed. But over the next sort of couple of decades, there's not really any major leaps forward necessarily in understanding how oxygen first arose, but there's more of an understanding that oxygen levels in our atmosphere are controlled by different systems on Earth, by the burial of carbon, by the burial of sulfur, and there are attempts to quantify and to model this and to try and work out what oxygen concentrations would have been over time. And then in the year 2000, I'll show this in more detail on the next slide, James Farquhar and a few others working in the United States make a big discovery. They discover mass independently fractionated sulfur isotopes, okay? Again, we'll talk a little bit about what this is. We don't need to worry about it too much, but the important thing to note is this is something that had only been noted in extraterrestrial materials before. This had never been seen on Earth, and it pointed towards the fact essentially that to have this kind of mass independent fractionation, we needed an atmosphere at some point that lacked oxygen almost entirely. And again, when they noted when that mass independent fractionation seemed to stop, it roughly tied with this 2.3 kind of period of oxy-atmosversion. And a couple of years later, people managed to quantify that to that level of oxygen that would cause that change in sulfur isotope systems to a minute amount of oxygen, 10 to the -5, the levels that exist in our current atmosphere. Tiny, but enough to cause all kinds of mischief, all the kinds of mischief that these geologists have been noticing for the last 80 years. And so it's only about 15 years ago that Dick Holland coins this term that we use to refer to this now in sort of common parlance, which is the Great Oxidation Event. And since then, well, we have broadly extended the Great Oxidation Event to like a 500 million year period. And we have more redox proxies, that is to say, geochemical tools that we can use to trace oxygen levels in our oceans and in our atmosphere. Now, I'll just make a quick point about this because this is something I spend a lot of time thinking about as sulfur isotopes, and I really think it's quite an elegant example of how we can see such a fundamental shift in the Earth system. So let's not worry too much about the isotopes because isotopes are fiddly and confusing. Trust me, that's my day job. But you can see quite clearly, you don't need to have a detailed understanding of isotopes to see that when we look at these sulfur systems, we're really comparing between 4 isotopes of sulfur in this axis. We see a wide spread in values, and then suddenly it drops down to nearly 0. Now this is because when it goes down to 0, this sulfur starts behaving in a way that makes sense. The isotopes appear in shales, in pyrites, in ratios to one another that make sense with thermodynamics. It doesn't make sense over here. We call this, it doesn't make sense. It's not predictable. The different isotopes are not appearing relative to each other in any systematic way, and we call that mass-independent fractionation. It's just a scatter, but there's a systematic basis to it, but it does appear as a scatter. And so what we can see is basically that we had two sulfur cycles, one where prior to about 2.5 billion years ago, sulfur dioxide from volcanoes was emitted into our atmosphere. It interacted with solar ultraviolet radiation, basically got split up into different aerosols. And those aerosols either carried a negative signal, so this half of the graph, or a positive signal, this half of the graph. And most importantly, they were kept separate in an atmosphere that lacked oxygen. And so we got this wide scatter. But after oxygen rose in our atmosphere, basically this system was shut down. It still happened, but this pathway, these reduced aerosols, they were keen to react with any trace oxygen in the atmosphere. They formed sulfate, just like in this pathway. And essentially, if you imagine this was -1, this was +1, they cancel out to give you 0. And so this is the way that these sulfur isotopes, this smoking gun, was discovered, that shows how our atmosphere evolved into an anoxic state. Just before the Great Oxidation event, it is worth saying, of course, that things were a little bit contentious. We don't know exactly when oxygen started to rise to levels that started to leak into our atmosphere, because all oxygen was produced in the shallow oceans by these stromatolitic communities, by these microbial mats. And so this would have looked a little bit like this, with the water coming, the oxygen bubbling off. And we called these areas where the shallow water was oxygenated oxygen oases, because they were oases of oxygenation and overall a reduced anoxic sea. Was it leaking into the atmosphere? Oops. There's a couple of different thoughts on this. Evidence suggests that certain trace metal concentrations in shales seem to suggest that it was happening, and that those trace element concentrations would only be possible in an environment where we had oxidative weathering, which suggests oxygen in the atmosphere. And this is called the so-called whiff hypothesis, whiffs of oxygen prior to the Great Oxidation event, if not full oxygenation of the atmosphere. Others, including folks I work with at St Andrews, would argue that no, the atmosphere remained completely anoxic and actually oscillated between periods where it was clearer and periods when it had an awful lot of organic haze in it, and that these haze events may have actually helped to oxidize the earth too, by the breakdown of methane, and that creates hydrogen which escapes into space. And as you lose hydrogen from the earth, generally speaking, that means you oxidize the whole system. So why did it happen when it did? Well, if you can answer this question, you're doing better than me, and you're doing a bit better than most of us, and it's a bit of a horrendous read, but there are papers on this, and you're welcome. I'm welcome to have a chat about it. But generally speaking, the way that we think about this is that there were sources of oxygen and there were sinks of oxygen, and around about, even though we had oxygen production from cyanobacteria as early as 2.7 billion years ago, at 2.5, the balance between sinks and sources shifted in favor of sources. So I've kind of crudely demonstrated this with a seesaw, but this meant that essentially oxygen started to rise, and we started to see those changes, for example, in atmospheric sulfur cycling and in other systems as well. That gives us that fingerprint of our oxygen-rich atmosphere starting to evolve, not quite there yet. But the reasons, the different processes, the different sinks, they're all related, generally speaking. I've listed a few of them here, but I'm not going to go through them. But basically, they relate to essentially the efficiency and the timing of the evolution of oxygenic photosynthesis. Those are your life reasons. And then there are some tectonic reasons, the growth of our continents and the changes in how volcanism is occurring and what's being emitted. And that's also related to how our planet is evolving as well. Now, I mentioned that what these early workers kind of noticed was that associated with all of these changes, there were major glacial deposits, and so these are sometimes referred to as the Huronian glaciations, and this is named after the Huronian supergroup, which you'll find in southern Ontario in Canada, but you find these glacial deposits worldwide in North and South America, Southern Africa, Russia, Australia, China, and India. And here I have an example of the Makanyeni diamictite, which is the first snowball earth deposit from South Africa. How do we know it's a snowball earth deposit? That's a very good question. Snowball earth is one of these pan-glaciations, a whole worldwide global glaciation. The reason that we think that the Makanyeni was one of these snowball earth deposits that coincides with the Great Oxidation Event is that at the top of that diamictite there are lavas, and the lavas are closely associated with the diamictite. They are deposited or extruded and deposited roughly the same time, and those have been dated quite accurately recently, and they have also had a paleomagnetic analysis done that shows that they were extruded at low latitudes in the tropics and near to the equator. But then we also have glacial deposits in the tropics and near to the equator, and that's only possible in a scenario where we have a very, very widespread glaciation. Which caused which? We don't really, well, we didn't really know. There were two kind of hypotheses: that the rise of oxygen caused a destabilization of the greenhouse effect. Now, when we were talking about the faint young sun, we talked about an enhanced greenhouse effect composed of carbon dioxide and methane. The methane is generally unstable in an atmosphere with oxygen, significant oxygen in it, and the residence time of methane would drop, and this, it's thought, would have caused a cooling and a glaciation. The other argument that was put forward was that the glaciation, that during the deglacial phase, because the glaciers would have ground up the continents, they would have delivered an awful lot of fresh material into the shallow and nutrients into the shallow marine settings, and this could have caused a sudden bloom of cyanobacteria and of oxygen production. And we didn't really know which of these was the case. It was kind of a chicken and egg issue, because we didn't really know when atmospheric oxygenation had happened relative to each of these glaciations. And of course, the only one of these glacial deposits, to add even more uncertainty, that we knew for sure came from the low latitudes was the Makanyeni. Well, earlier this year, I added my threw my hat into this particular argument, and that is to say that we analyzed some rocks from Russia, and that were very well dated, and we found that some of these had the mass independent sulfur signal, that big scatter sulfur signal that related to an anoxic atmosphere, an atmosphere lacking oxygen, and then the rocks from the overlying succession, they possessed the sulfur isotopic signal, which suggested that the atmosphere had gained trace oxygen. So we concluded that atmospheric oxygenation had happened sometime between these two. We also knew from a couple of years previously from someone else's work that we knew exactly when that snowball earth deposit had been laid down. And so with the age control that we have had just in the last couple of years, we were able to say, well, actually there's a global window where we can have atmospheric oxygenation, and it is distinct and prior to that snowball earth deposit. And so I think that this chicken and egg issue has kind of been resolved. Who knows? Many might disagree, but I think that we now know that the atmospheric oxygenation triggered the glaciation. And others think that too, and independently of our work, and this is related to the fact that when you push a flux of oxygen into the atmosphere, it decreases that methane residence time, methane levels drop, and you can quite quickly, not instantaneously, but very, very quick timescales, you can cause a cooling of up to 10 degrees, and that's more than enough to really plunge the planet into very pronounced severe glaciation. Now, a little bit more about oxygen. You're probably bored of oxygen, but oxygen actually creates another gas which we have to think about, which is ozone. Once you build up oxygen in our atmosphere to fairly significant concentrations, that oxygen itself undergoes interaction with solar UV radiation. It breaks down, forms photochemical radicals which collide with more oxygen, and the end product is O3, or ozone. ozone then further collides with more radicals, produces oxygen, and it's an endless cycle of creation and destruction called the Chapman reactions. And this is what's happening today above our heads in the ozone layer. And what's important is that that ozone layer acts as a barrier to more incoming solar UV. It acts as a shield. So establishing when that ozone layer formed is important for understanding surface habitability and the kind of flux of solar radiation into the lower atmosphere. During those Chapman reactions, we have another kind of mass-independent fractionation, something that happens in oxygen. And we monitor this with what's called the triple oxygen isotope signature. Now, we don't need to worry too much about that, but essentially a negative cap delta 17O value, cap delta 17O being what we use to refer to this triple oxygen isotope anomaly. This negative cap delta 17O value gets passed into oxygen in these Chapman reactions. The magnitude of that value depends directly on oxygen concentrations, carbon dioxide concentrations, and the productivity of the biosphere, breathing basically on big scales, breathing in of oxygen and breathing out of carbon dioxide, and breathing in of carbon and photosynthetic intake of carbon dioxide and expulsion of oxygen. All of these things together control this value. And this value in oxygen, and this oxygen and this value can be transferred into rocks, and we can measure this over time. And this is kind of cutting edge. This has been really only coming through in the last 10 years or so. And so through sulfide weathering, we can get this signal into minerals, sulfate minerals like gypsum and hydrite and barite. And so our first detection of these negative cap delta 17O anomalies can give us a direct atmospheric fingerprint. There's no other way to generate these values, no abiotic way, no non-atmospheric way to generate these signals. They tell us directly about the atmosphere, and when we can measure them in sulfates, which we did in sulfates about 2 billion years old a couple of years ago, we put our first firm fingerprint on when the ozone layer had formed. And so I think that's pretty cool. And this is what I kind of work with a lot now, using these direct fingerprints of atmospheric compositions to kind of back calculate oxygen, carbon, and primary productivity levels. So to summarize with oxygen then a little bit, the deep time picture. We had very little oxygen prior to 2.5 billion years ago, bar the debated WIFs and the periodic hazes, and then we had the great oxidation event between 2.5 and 2 billion years ago. And atmospheric oxygenation, we think, using our evidence from Russia more precisely in a 70 million year interval between 2.5 and 2.43 billion years ago. We know we had an ozone layer created from that oxygen buildup from 2 billion years ago, though some have more recently argued that about 2.3 billion years ago, though I'm not entirely sure. And then, we'll not talk too much about this, I'll skip this in the interest of time, but possibly a little oxygen production is probably getting a little bit too big for its boots, and there was a bit of an overshoot, though we're not entirely sure what that signal means. The level through most of Earth history is then kind of debated, this showing the unfairly called boring billion. And then there's another rise in the Neoproterozoic when we also have other snowball Earth events, and in the early Paleoproterozoic is the most recent proposal, the PO, the early Paleoproterozoic oxygenation event. Throughout the Phanerozoic, oxygen levels are fiercely contested. We don't know exactly how they've gone, but our thinking has changed radically in the last 10 years. When we thought oxygen levels were roughly round about what they were today, and possibly gained very high levels during the Carboniferous before sinking down a bit. This is kind of work done by Bob Burner and others. Now we really think that there's a bit more of a case to say that oxygen levels remained low until the end of the Silurian, and then jumped up to levels closer to the modern during the Carboniferous, the Permian, and the Triassic, before decreasing a little bit, and stayed high through the Mesozoic. And this is something that we're working on ourselves at St Andrews, using this cap delta 17O anomaly I mentioned a few slides ago. We are looking at these negative values, and we're trying to tie them back by combining them with modeling to the concentrations of oxygen, carbon dioxide, the productivity of the biosphere. And the circle data, which links quite nicely to the Scottish Geological Trust, talking about Scottish rocks. I've talked quite generally, this is general interest talk. But I want to give some shout out to Scottish rocks, Scottish geology. We have been working on Scottish geology. We've got a nice signal, negative signal actually from the Aberfildy barite deposits. That's something we're trying to understand that. But this circle data comes from the early Mississippian, from the early Carboniferous, and it's from a range of different successions. We've looked at 3 successions from slightly different paleo-environmental settings across the UK, from the Ballycultra Formation in Northern Ireland to the Middleton Dale and Hydrate Formation in Derbyshire. But I think the one that's particularly interesting is the Ballahan Formation from Berwickshire. And so what we have here are a really interesting sort of series of coastal wetland deposits, which are associated famously with the first tetrapods and this phenomenon known as Romer's Gap, which is a postulated gap that was thought to exist in the fossil record of tetrapods, the first organisms on land and the first really to breathe air, first animals, to breathe air rather than insects. What we've noted are the most negative cap delta 17O values measured in the Phanerozoic. And what we hope to do, even though Romer's Gap itself has disappeared, we know it's a bias of fossil collection now. But for a long time, because this gap supposedly existed in the fossil record, there was a lot of discussion and debate about what it might be. And a lot of people thought, or some people thought, it may have been due to lower or contested oxygen concentrations. So there's this legacy debate about the atmosphere at this time. And so this is what we're kind of hoping that our new data will finally put to rest, what the different concentrations were of different gases at this time using this oxygen isotope data. So we're excited for that, and that will be hopefully coming through in the next year or so. And just to finish off with our last gases, carbon dioxide. I haven't talked much about that because lots of people talk about carbon dioxide. Usually talk about carbon dioxide from the point of view of modern climate change, or climate change over the last 2 million years. But gradually over Earth time, our feeling is that the carbon dioxide levels have generally decreased. They've generally gone down to, and then this is where we have more sensitive data here. This is where we classic Precambrian geology, broad curves. The consequence of this, though, carbon dioxide has major consequences outside anthropogenic global warming changes and many things and many aspects of climate, but it also relates to the so-called snowball glaciations. Now, I'm not going to talk too much about this because I'm aware there is a talk by Tony Prave in a couple of weeks, and he'll probably talk about this far more than me. But essentially, these later snowballs, rather than our Paleoproterozoic snowball 2.4 billion years ago, which was related to oxygenation and methane crash, this is related to tectonics. This is related to the fact that we had a lot of landmass in the late Neoproterozoic that was around the equator. We had a lot of flood volcanism, and we had a lot of weathering, silicate weathering of that fresh volcanic material and intense tropical setting that brought down CO2, weakened the greenhouse. We had a slightly fainter sun, and all of this promoted ice sheet growth, and the growth of those ice sheets then introduced another feedback by increasing planetary albedo, and cooling continued and ran away. And so this kind of snowball, these kind of second and third snowballs are tied more closely to enhanced carbon dioxide drawdown. So as well as heating things up, carbon dioxide, if it goes the wrong way, can cool things down quite a lot. It's a very, very sensitive gas in our atmosphere for controlling our climate. And we can actually trace, or we think we can trace, how much carbon dioxide it takes to break out of a snowball by, again, looking at our friend here, the cap delta 17O anomaly, which some of the most pronounced anomalies in Earth history occur in association with these snowball Earths. And we think that colleagues have proposed that may relate to very, very high CO2 levels up to about 12,000 ppm, but that's yet to be seen. And that's something that the group here at St Andrews is working on and delving into a bit more. So to put it all together, basically nitrogen, we're not really entirely sure about the early history of nitrogen. We know that at least from about 2.5 billion years ago, it's probably been gradually rising, and it is our principal control on atmospheric pressure. Oxygen has probably the most dynamic history of all, and it affects and alters all of the other gases. That's why I think it's the most important, but I'm biased. We know that there was basically no oxygen prior to about 2.5 billion years ago. It was hard to put constraints on that. Then it shot up during the Great Oxidation Event 2.5 to 2.4 billion years ago, and then again at the end of the Neoproterozoic and the Paleozoic. CO2 levels have gradually been going down, and as have methane. Methane took a particularly large crash during the Great Oxidation Event. But both of these greenhouse gases continue, even in small concentrations, to exert strong controls on our climate. And why is this important? I think that this is an important point to kind of finish on, really. We are very soon going to be probing the atmospheres of other worlds. And we are going to be doing that we can do that now, but we are going to be doing that in greater detail when certain telescopes, orbital telescopes and large telescopes come online in the next decade. And the James Webb Telescope, for instance, which is this kind of guy down here on the right, will do this hopefully from 2021, touch wood. The number of exoplanets that we are finding is astronomical, and many of those look like Earth, and many of them exist in what we call the habitable zone, this perfect zone where liquid water can exist between just, not too hot, not too cold, Goldilocks zone, just right. And so we are thinking that we can possibly start probing the atmosphere of these planets and looking for evidence remotely that some of these planets may have life. And this is why it's really important that we understand how our atmosphere looked at different times, because we know how that atmosphere looked, and we also have an independent rock record of life and of processes. So that is why this deep time understanding of our climate is important. It's so that we can basically make best guesses about where to look, where to concentrate our kind of have limited resources and remote detection technology, and try to find out where we may or may not find life. And hopefully something as well to take home by looking at change in our atmosphere over time, it changes our perspective. Habitability isn't just a zone around a star, it's also a time. If we were looking back at the Earth during a haze event 2.4 billion years ago, if we were looking back at it during a snowball Earth, if we were looking back at it during crazy high CO2 levels, would we have recognized a habitable world? I'm not entirely sure that we would have. So we need to bear in mind that, unfortunately, we will not just have to look at just a tiny fraction of worlds. We will have to recognize that we're looking at them in time, and if we rule them out, we may be passing by a gem. We don't know. So with that, I will basically conclude, because I kind of said this anyway, and I know there's another talk at 7. So I will conclude there, and I will say thank you very much, and thank you for having me.